few cross-interdisciplinary talks, and so along the similar lines, let us continue with that, and let us hear from Jonas, meteorological aspects on Jupiter. Thank you.
Yeah, so this is, the subject today has nothing to do with the prediction on effect assimilation, so I was actually not planning to talk about it. But then after, on Tuesday, there was discussion between solar physicists and meteorologists about convection and general circulation, so I thought that this perhaps could, maybe there is a good audience for this kind of talk here. Anyway, so the question is to explain these zonal flows on Jupiter. So this is a picture, satellite picture of Jupiter. You have probably all seen this kind of picture before. These are various colors, and they are connected with a zonal wind pattern. Here, by the way, is this famous red spot of Jupiter, which is a big vortex, and all these sort of circular or oval spots here are in fact vortices, and there's a lot of work have been devoted also to understand these vortices, but I will only talk about the zonal flows today. So, this exists not only on Jupiter, but also, for instance, on Saturn. Here, so you also see these zonal bands here, and they are connected to the manifestation of zonal wind pattern on Saturn as well. And there also exists some less pronounced zonal wind pattern on Neptune, in fact. And here is a picture of this is a zonal mean wind that has been obtained by basically, I think, cloud tracking from satellites on Jupiter. So you can see that there is a big eastward jet near the equator, so this is superrotation. I think someone referred to that on other cases the other day. And then there is this alternating zonal wind. And they also put in here positions of various famous vortices. The question is how to understand this then. Why do we have this? I think you could say that perhaps the first serious attempt to do some kind of modeling of this was done by Garrett Williams in 1979. And he did a very simple simulation, or used a very simple fluid modeling. This is just two-dimensional Navier-Stokes equations. That is, on the left-hand side, we simply have a direction of potential vorticity, or actually total vorticity in this case. So here is relative vorticity, and this contribution here comes from the rotation of the planet. So this is the simplest possible equation you can have for modeling large-scale flow on a planet. On the right-hand side, we then have various terms here. D is this is a forcing term, some kind of random forcing, and then this is lateral viscosity. This is supposed this is lateral viscosity. This is supposed to represent here bottom friction, some kind of rail friction term. So what he did then was to run this and see what happened. And so this is a picture. So this was the initial state, and I think probably this reflects the forcing term. I'm not quite sure here. I should say that mention maybe I should say maybe the reason why I have used transparencies here is that this is in fact I was interested in this in the beginning of the 90s maybe. So these transparencies are from a talk I gave at EGU in '96 I think. So this has been sort of dormant, this subject. And then we took it up a little 1 year ago. So I haven't actually talked about this since '96. Anyway, so here is the initial state, and then you can see the development here, and at the end you see really a rather nice zonal wind pattern here. So this, what's shown here is a stream function. So the contours here are streamlines, and well, we really have a zonal wind pattern. Here is the zonal average. So of course this looks convincing. I mean, there must be something in this that tells something about Jupiter.
Plus and minus, you can't really distinguish, right?
Sorry?
Plus and minus in the upper right B and B for the stream function? Must be plus and minus alternating, right?
I don't know. Well, of course, I can't say here. Well, you could say here that here clearly they have superrotation very close to the equator.
So how is this force? Is it
Some random. I don't know if it's actually a regular small-scale forcing or if it's just random. But it's anyway, I'm sure that the forcing is small-scale, so that these zonal jets, it does not match the forcing pole. I mean, it's something that is spontaneously generated by the flow. So what is happening here? Well, I think at least to metrologists, oceanographers, in some sense this is not very surprising. And clearly what's happening, the only physics that really is in this simple model is the beta effect. And well, I think everyone who is in metrology and oceanography knows, of course, what beta effect is. I'm not so sure about the solar physicist, so maybe I can explain a little. This is the effect of the fact that the Coriolis parameter varies with latitude. So I have to speak about this. No. Okay. Explain with that things. Yeah. Okay.
We normally don't make an assumption of thin layers, and therefore we have just have only a pursuit directly included.
Okay. Anyway, I mean, the fact is that what matters is only the projection of the vertical direction of the Coriolis or the Earth rotation, and that varies with latitude. And basically, what that effect does is that it's a strong. I mean, it inhibits large north-south excursions of fluid parcels, and that's well known. And there's a kind of you can think of it as a kind of restoring force, and the result of that restoring force, for instance, is Rossby waves.
And can you actually get the Rossby waves even in a Cartesian model? I mean, beta effect is good if you are even.
This is spherical geometry. Clearly, in this model, you have Rossby waves. I mean, these undulations that you could see in the pictures, they are basically Rossby waves.
So I mean, it looks actually circular. It was circular geometry, right?
This was circular geometry, yes. Yeah. And so in the circular geometry, this beta effect is built in automatically, of course. You have to sort of put it by hand if you have a Cartesian coordinate system, but you can do that as well. So I would say that Rossby waves is basically almost the only, well, it's definitely the only waves that exist in this simple model, and it's sort of the main physics that exists here. So clearly, beta effect is a key part of explaining the zonal jets. But one cannot really be satisfied with the way this flow here is forced. I mean, everyone agrees that somehow heating, and in particular convection, is somehow driving, forcing the flow on Jupiter. And this way of representing as some kind of random mechanical forcing is really true, of course. So what we want to do here is to include also in some self-consistent way convection in the picture of these zonal flows here. So beta effect is one aspect, but then we have to sort of couple these to convection in some ways that make sense. And you can think really of two different, principally different kinds of convection. One is, I would say, sideways. This is what we have on Earth and on Venus and on Mars. So the main heating comes from the Sun, and the Sun, of course, heats the tropics much more than the polar regions. So the main driving force of the circulation on Earth is this horizontal temperature gradient. The other paradigm here is, I would say, vertical convection here. That means that you have heat flux from below. That's the famous, I mean, the most basic example would be really with canal convection, where you put a pan on the dish pan on the stove and you heat from below and you see convection. That's vertical convection. Heat coming from interior here. And there are, I believe that it's a principal thing here that on Jupiter we really have this vertical convection. I would say not everyone would agree with this, but that's my stance working this. And there are some arguments I have for believing that it's a crucial thing to have these zonal flows, that you have really this vertical convection case. First of all, there is no zonal flow like this alternating zonal bands on the terrestrial planets, which are heated by the sun, like on Earth, Mars, and Venus. There is some, of course, some zonal pattern on Earth, but it's basically just, how do you say, one jet at the equator and then mid-latitudes the other way. So it's not really a alternating zonal band. It's also much more irregular. Another argument.
Very different.
Sorry?
The Rossby number is very different. Is that not continuous transition as you bring the Rossby number further and further down that you would get into that?
I think the Rossby number, I guess, is small, typically for the large-scale flow on all planets.
Yeah,
perhaps with the exception of Venus.
Yeah.
I mean, you can see multiple jets in the ocean.
Yeah, Well, I mean, in some cases, there are many cases where people can claim to see jets, but that is typically after averaging. I mean, if you look at the instantaneous field, you have a lot of irregular flow, and then if you do a heavy averaging, then you can see zonal jets. I mean, then I agree we can see that in the ocean and in some experiments. That is, I think, not at all what we're seeing in Jupiter. This zonal flow is dominating. I mean, it's immediately apparent in any instantaneous flow field. So it's really, I think, a different thing.
Yeah. Also you have topography. In the south hemisphere near the pole, south pole, you have a very stable jet.
Yeah.
So
on Earth, you mean? Oh, you're talking about the ACC?
The atmosphere and in the ocean.
Okay, yeah.
So it's also
Okay. Still, I would claim that this, I mean, the zonal flow pattern we see on Jupiter and Saturn, I mean, this striking, very strong and regular mean flow. This is something that is connected to planets which are really dominated by the vertical heat flux, heated from below.
Yeah, I would actually take issue.
Sorry?
I would actually take issue with that.
Okay.
I mean, I think you have one jet on Earth, and that's it, or maybe two.
Yeah. You would take issue with what?
With no zonal flow on Earth. I mean,
yeah, you have one. Okay, but that's. I would say that
Jupiter is big, so you have more.
Yeah. Okay. Yeah. Okay. So let's just go on here. Another argument for this, I think, is that to think that at least on Jupiter and Saturn, the sort of the key thing is really that they are heated from below. Is that there is a very small equator to pole heat difference on these planets which have these striking zonal flows. That's of course very different from Mars or the Earth. So here I just sketched what it looks like here. So you can see on these giant planets there's almost no lateral or meridional temporal gradients at all. The main undulations are in fact connected with these zonal jets, not with the equator to pole difference here.
Is there any argument which could be put forward in favor of solar heating playing a dominant role in this evolution?
Not really.
it's a
No.
thermal.
All the evidence is in favor
Yeah.
of vertical convection being the...
I think so.
Yeah.
I'm just I'm making my point here. Trying
Of
to
course,
think.
solar heating is playing a key role. It's a thermal wind.
I mean, if you look at there is of course a zonal heat flux on Jupiter, which is not insignificant. I mean, the interior heat flux is bigger, but not by more than I don't know, a factor of 2 or something. So it's not you can't offhand just say that solar heating is not important. I believe it's not so important to get these zonal jets, but it's not obvious.
No, it's, I don't agree at all with that statement.
Sorry?
I don't agree at all with that statement. You have the thermal wind equation. This thermal wind equation has to be realized. You have a variation of the heat as a function of latitude. Then you have dV5 over dz is equal
No, of
to
course,
the term.
this is thermal wind. I mean, I'm trying in this sketch here. There is variations of the temperature with latitude, and this is thermal wind. It's connected to the zonal jets. The point I'm making here is just that the main. If you want to think of explaining these zonal jets, we can really forget about the sun. It depends on the heat coming from below. That's the point I'm making. And so, for the rest of the talk, I will forget about the sun. Let's say like that. Okay, so what we have to do is then to think about something that's typically called rotating convection. Okay, so we can think of heating some fluid from below, and the whole system is rotating. So let's talk about that a little. And this is one of the classical fluid dynamics problems here. And you have 3 dimensionless numbers here. Prandtl number, that's the ratio between viscosity and heat diffusion. And then Taylor number, kind of measure of rotation speed here. And then the Rayleigh flux number. You could also say that this is a measure of temperature difference, essentially. Here it's stated in terms of heat flux rather than temperature difference. Anyway, so you can combine these to get one number which is independent of dissipation. I mean, if you don't have rotation, you don't really have that. Then you have only this one and the Rayleigh number, and they are both, well, okay, this is not independent. This is a ratio between dissipations. But this Rayleigh number, that goes to infinity as dissipation goes to 0. So, but here we have really one number which is independent of dissipation, which means that you can have sort of different regimes depending on how strong rotation is compared in some sense to the thermal forcing.
Is Is your phi actually the actual heat flux, or is it the one that you would have had in a hydrostatic equilibrium?
No, I think this is the actual heat flux here.
Then it's not. Then it's a different range.
But you could of course rephrase this in terms of temperature difference if you wanted to.
Yeah, but this radio number is much smaller than it would be if you had a unstably solidified.
Actually, I'm not. As I said, I mean, I haven't actually looked at this for 15 years, so I'm not 100% sure about this, and it's not. It's not really essential here. So, I mean, typically, of course, we have a very large scales here. So we want dissipation rates or the diffusion coefficients and the viscosity coefficients. They are, let's say, infinitely small almost. So, of course, both these numbers go to infinity here. If you look at large scale flow on Jupiter, but we can still have then a finite, what I call here Rossby number, natural Rossby number, which is then, in some sense, a comparison between heat flux and rotation. And you could think of this as a measure of relative vorticity from the typical velocity fluctuations that would be generated by this convection here. Anyway, we want to have then very large Taylor number and Rayleigh flux number here, but we want to have a Rossby number which is small, not as small as these are large. I mean, these go basically to infinity. But typically for large scale flow, we expect some kind of Rossby number to be small, but not very small, maybe 10% or something. That's what we have on Earth, maybe 0.2 or whatever. So let's look at a very simple stability diagram that can be done from linear stability analysis here. This was done by Chandra-Sekhar, as followed. So here we have these numbers which we want to go to infinity basically, and then the ratio between these two determines whether Rossby number then is large or small. And really the point here, so we have this line here, which it turns out for the linear stability analysis at least, the main conclusion here is really just that if you have large enough rotation compared to the heat flux, then the whole thing is stable. Of course, if you have zero rotation, it's basically always unstable. You heat from below and you need very small heat flux to destabilize it and you get convection. But you can stabilize that by you can always stabilize it if you spin the system quickly enough. So that, in fact, you have no instability, although you have warm fluid below cold fluid, it doesn't destabilize, and all you get is molecular heat diffusion. So fundamentally, rotation is a stabilizing effect here. That's the main point. Okay. So, what does it look like then? Well, I found in the literature some people who did experiments with rotating convection, Bubnov and Galitzin, and I think there are also several others, but this is one I found first. So what they have here is a fairly small vessel here. This is just 17 centimeters. No, so this is 3 decimeters, something like that, and the height is 2 decimeters. Pi is not, pi is radius, not. This is actually diameter, it looks like. Well, anyway, a small laboratory vessel here, and it's heated from below, insulated on the sides, and then there is air here, so the cooling is mainly by evaporation from the surface. And then they spin the whole thing and look at the flow. So very simple classical experiment here.
Yeah, the Space Lab 3 experiment was done with spherical vessel.
Okay, yep.
Aboard the shuttle, I think, and by
I think I have it.
And Tounet and Gassmeyer.
Okay. I have one of my last transparencies is from experiments similar to that, so I'll mention that later. So anyway, this is what it looks like. So what they have here, they put some dye which then concentrates into these small vortices, and you get this beautifully looking pattern, or a regular pattern of small vortices. So these are all small convection cells where the fluid sort of spirals upward, and then maybe in the middle, or I don't know if it's in the middle. The whole thing is really symmetric here. There's no difference between both. I mean, there's no, it's symmetric between warm and cold and up and down. So anyway, you can think of the warm fluid going up in the spiral, maybe in the center, and then spiraling down around the center. And it's a lot of small convection cells. So So of course there is no zonal flow here. But then there was one other figure that caught my attention in this paper, is this one. And this is the initial stage. So what they do is actually that they, if I remember correctly, what they have, they start spinning the whole system here. And in the initial stages, the dye collects into rings like that. And in fact, this is a sort of a ring-like convection cells. So, because of thermal wind, of course, what we have here is in fact a system of zonal flows. But then rather quickly this becomes unstable. It looks like typical shear flow stability. And then it falls apart and you get these singular small cells. So my idea was that perhaps...
The fix is the top of the fluid forming a parabola? I mean, is there a beater?
Yeah, there is a parabola, of course.
So there's a beater effect.
There is a beta. Well, there is a weak beta. I don't think this is spinning very freely, but there is a weak beta effect from this. And what they could see, by the way, also was, which is interesting, then, is that the quicker you spun this, the larger the rotation rate, the thinner these convection cells become. If you have very small rotation, basically the aspect ratio of convection is unity. But then they become thinner and thinner, so the aspect ratio between width and height is smaller and smaller the quicker you rotate. Anyway,
these are rings then, yeah?
These are rings, yeah, these are rings. And what is happening here is that...
And these marks are the downfall...
This is dye. Dye collects into these rings. So that means that it's convergent on top.
Yes.
I think the dye is on top.
Yes.
And then there is downwelling. Right? And so this dye collects here. So really you have here, and of course so you have organized convection cells in these zonal rings. And then of course it has to be a alternating zonal flow, although they didn't measure that. But it has to be by thermal wind.
Yes, and what is the, and then as you increase the radial number and keep the Taylor number constant, or what?
Yeah, if you rotate it quicker, then these rings become more narrow and this pattern becomes more dense.
But then it should become more eventually stable again.
Well, they never observed any stable. I mean, the end state, the final state in their experiment was always a pattern of single cells like that. But my idea was then that, well, what is missing? Here we have rotating convection, but we're missing one thing to have the zonal flow. We miss the beta effect. So let's put in the beta effect into this experiment. Okay. So I got someone to build this for me. So present, no longer present experiment. Past experiment, 1994. Anyway, so to combine this experiment they had with a topographic beta effect. And this is the typical way that people do if they don't, I mean, it's difficult to have a varying Coriolis force in a lab experiment. So typically what you do is to have a varying topography instead. To see if this could perhaps stabilize this convection pattern. I mean, they actually do see here a zonal jet pattern, and we know that beta effect can stabilize zonal flows. So perhaps this will be. And well, one way to look at this stabilization is to look at this. So this is potential vorticity, and if you have a large, and the stability criterion for a zonal flow to be stable is that this should be a monotonic function, this Q here. So if you add a large beta effect here, then eventually any flow becomes stable. So in principle, there could be a hope that it could stabilize this flow by adding a beta effect. So in this experiment here, this is what the apparatus looked like. So we have here some kind of vessel here with insulation on the sides. This is cylindrical. And then I put in a conical bottom like that. And the whole bottom here is by metal. And then there are 4 strong lamps here heating the bottom surface. And this was done so we didn't need any electronics in the rotating system. It's a very simple thing. And there was also a thermometer here. I could measure the temperature here, and I could measure the temperature in the air, so I had some idea of the heat flux of the temperature difference. And then in some of the experiments, I also added a thin plastic lid like that. Because that is because essentially, if we have a barotropic flow, we have sort of homogeneous horizontal velocity of the water column, then it's enough to have topography on the bottom to have a good beta effect. But if you have baroclinic flow or some vertical structure, that it's only really the bottom layer or lower half that feels the bottom topography. So I decided that to really have a good try, it's better to have beta effect from above as well. On the other hand, of course, you have a smaller heat flux then, but so I tried with both. Yeah, okay, and the heat flux was measured then by monitoring, so I put on an insulating lid, and then I could measure how quickly the temperature rose, so that gives some idea of that. Well, unfortunately, this experiment failed. No matter how hard I tried, how quickly I rotated, the result was always the same as Bornov and Galizio. I could never stabilize this on the flow. Nevertheless, I think I want to show at least some figure from this experiment, although it was a failure. So this is my pictures. Basically reduce the results here. Initially there is this kind of normal flow pattern. But then after a while, here you can read the time off here, which not seen very clearly. As you can see, these destabilize, you get some kind of instability, and in the end, you just have a collection of more or less point vortices. Sometimes a regular array, sometimes not.
Do you have kind of a polygon?
Sorry?
The center one? Do you think you have
Polygon. Here.
No, up
Here.
there.
Well, this is the initial stages of instability. Sometimes you can get a rather regular pattern of vortices, sometimes not. Yeah, of course, initially it's the most regular stage.
Because of course we have a polygon that looks like that on the south pole of Saturn, which is interesting.
Yeah. Yeah, I don't know. I never really tried to see exactly what kind of. For instance, you could try to understand how many vortices you have around from some stability theory. I never tried to do that. So basically this experiment then was a failure. And that's why I actually never published this. Other people later have actually tried to do the same thing. And here is an experiment by Peter Reed. So they had more heavy experimental apparatus. They did an experiment on the big Coriolis platform, which is 18 meters in diameter in Grenoble, like a rotating platform. And so they have here, same idea here, they have a topography on the bottom, a beta effect, and then they have water, and then they spray the water with salt from above. So that means that the water is heavier above, and then they can have convection. And they claim then to sort of explain the zonal flows in Jupiter. I would disagree with this, because this is an instantaneous flow pattern here. And what you see is a rather chaotic, irregular flow pattern. And if you average over a long time, then you can see some zonal flows appearing. But I would say this is really not what we see on Jupiter. On Jupiter we see an instantaneous flow field, which is obviously zonal. The zonal component is dominating. So basically, of course, they have a much, much bigger Reynolds number in this experiment, so therefore they don't have these regular vortices probably. But I think what they see is basically turbulence, rotating turbulence. They don't really see a zonal flow.
How big was your experiment?
My experiment was this big.
And this is a very huge.
Yeah, I mean the whole platform is, I think, is 18 meters, but and then they only used a section of that, but it's, I don't know, maybe a couple of meters or something. So what is missing then? Why doesn't it work? What is missing to have a real zonal flow here? And why? Well, first I'll explain the reason why I think we don't get a nice zonal flow in these experiments. Now, you can do some very simple estimates of what is needed for this topography to have a strong effect, this beta effect. Well, let's say that you move the fluid column to the side, okay? Then that induces this height difference, or the beta effect, that induces a change in relative vorticity. In order to really feel this beta effect, that change in relative vorticity has to be of the same magnitude as the Rossby number, essentially. So So the relative change in height has to be the same order as the Rossby number. And of course, we want these different vortices to feel each other, right? So in order for these small vortices to sort of feel the beta effect and join together into zonal flows, the beta effect, this change in relative vorticity, should be significant over the size of one vortex. Otherwise, they will just stay independent and continue to be single vortices. The problem is that, well, so I mean, when I did the experiment, I decided that, well, let's increase the rotation speed here. Right. If it gets small enough, then you can satisfy this inequality. The field, of course, the bigger the rotation, the stronger is the beta effect. It's just that the system cheats you. The system doesn't obey that, because what happens is that the stronger you rotate, the more narrow the vortex gets. And by some simple scaling, I came to the conclusion that this narrowing is exactly occurs in the rate that always beats you. It decreases about the same in the same rate as the beta effect increases, so that no matter how fast you rotate, you can never get the beta effect to be strong enough over the size of one vortex. So the convection cells, they are too thin and too tall to feel the beta effect. So what is then missing? What should we put into the picture? And I think that the answer is moisture. So that is where we talk about the rest here. And let's start with some basic things. You can tell me to skip this if it's obvious. I think what I will say now is obvious to people in metrology.
That is also connected with Jupiter?
Yes, this is connected to Jupiter. Yeah. But the concepts are well known and first undergraduate simple stuff in metrology, first or second course or something. And that is, we have something. Of course, I mean, on lab scale, you have convective instability. Simply means that you have warmer fluid below cold fluid. As soon as you have a negative temperature gradient like that, then you have instability. Now, on large scale, like in the atmosphere of the Earth, you have to take into account the adiabatic cooling. And you shouldn't compare with a vertical sort of constant temperature profile. You have to compare with an adiabatic profile like that. So if the temperature in the atmosphere decreases more quickly than the dry adiabat, then you have what's called absolute instability. And that is completely analogous to the usual instability that you have in Rayleigh-Benard convection. If the temperature decreases more slowly, then it's stable. So here we have on the bigger gradient than this one, or more quickly decreases. Then you have basically negative n squared, negative, well, imaginary voice of frequency. Here we have positive n squared. But if we then put moisture into the picture, things get a little more complicated. And then we have something else called a moist adiabat. Okay? What is happening is that suppose that you take an air parcel which is saturated in water vapor, 100% relative humidity. Then if you lift that, then some of this water will condense and release latent heat. And that of course continues. If you continue to raise this air parcel, heat will be released all the time. And the result is that you get the temperature will vary along, it will decrease more slowly along this moist adiabat. And so if you have a gradient which is between these two, then the atmosphere is what you call conditionally unstable. And what that means is that suppose that you have an air parcel that is at only 80% relative humidity, then it rises a little, well, no latent heat is released, and it just will sink back again if it's a small perturbation. And you have these regular internal waves with the buoyancy frequency. But if there is a finite size perturbation, I mean, if it's perturbed upward, the relative humidity, the absolute humidity is constant, but the relative humidity increases because it gets colder. And there is a finite threshold above which you hit 100% humidity. But then the air parcel will instead change its temperature along this moist adiabat. If then that is actually, this moist adiabat is more slow than the sort of ambient temperature gradient in the atmosphere, then you get instability. Although you have a positive buoyancy frequency, you in fact have instability. Yeah.
Is that you have a gradient in the mean molecular weight in this case?
Of what?
Or does the gas, total gas constant change? I mean, the gas constant divided by the mean molecular weight is what you have in the equation of state. P equals.
Yeah.
And does this have a gradient? This mean molecular weight is the question?
Yes,
Yes.
but it's not a big deal.
It's not a big deal. It's not this effect.
The
No,
effect,
it's
I mean,
not
this whole difference comes from the released latent heat
Yeah,
of
okay.
condensers.
Yeah, independent of the gradient. Yeah.
That has a slight destabilizing effect, but it's not phenomenal.
Yeah. Okay. Yes. Right.
I didn't quite follow that.
It's
I'm not
a
really
virtual, what do you call it, when you're a meteorologist, you call it a virtual temperature.
Yeah.
Okay. So anyway, in a moist atmosphere then, you have a kind of possibility for a finite amplitude instability that can be triggered by large perturbations. Okay. And in fact, this is, the convection in the atmosphere of the Earth actually is typically of this kind. And the sort of general large-scale average vertical temperature gradient in the troposphere is more or less the most adiabatic, and is regarded to be set in by convection, moist convection in the tropics. Isn't that true?
Yes.
Yeah. So typical convection in the atmosphere is not of this kind. I mean, you very rarely have absolutely unstable. You can have very occasionally an absolutely unstable atmosphere. But the typical case is